In this video, I want to talk about linear independence. This is again another topic from section 4.4. So linear independence. I think it's actually easier to talk about first linear dependence, so you can see what linear independence is not. So I'll explain. So I want to start very simply, and from now on, when I say vector, I want you to understand that I'm not necessarily talking about a vector in the plane, right? So we could be talking about, bad arrow there, we could be talking about some vector, something like that. So say some vector in R2, we could be talking about a vector in R3, we could be talking about a polynomial, we could be talking about a continuous function, because those are vector spaces. So from now on, when I say vector, what I mean is an element of a vector space. Okay, so just keep that in mind as we go along. So whenever I say a vector, I mean something in a vector space, even if it's not the usual Calc 3 or physics idea of a vector. So two vectors, I do think it's useful to start by thinking about vectors in terms of R2 and R3, but then we'll generalize. So two vectors are said to be linearly dependent. So linearly dependent. If, let's actually give these vectors names, because I think that would help. Let's call them U and V. So U and V are called linearly dependent if one is a multiple of the other. So if, for example, V is a multiple of U. Okay, so let me write what I said, because I said it better than I wrote it. But two vectors are linearly dependent if one vector is a multiple of the other. Okay. What this means, so say, for example, it could be that V is a multiple of U. So what this means is that if you think about this geometrically in terms of vectors in R2, two vectors are going to be linearly dependent if they lie along the same line. So it's possible that one is a multiple of the other, maybe it's half of it. Maybe the vector V is, some large multiple of U. Maybe it's a negative multiple of U. But if it's along that same line, we're going to say that they're linearly dependent. Okay, so those are all examples. So again, it is helpful to think about vectors starting in R2, but then we're going to generalize to more general vector spaces. That's what linear dependence is for two vectors. But really, we want to talk about linear dependence for lots of vectors. So let's bump it up to three vectors, and then from there we can generalize. So three vectors, say U, V, and W, are going to be called linearly dependent. So they're going to be called linearly dependent if one of the vectors is a linear combination of the others. So there's a linear combination of the others. This in general is what we mean when we say linearly dependent, is that one of them is a linear combination of the others. Generally, if one of them is a linear combination of the others, then most of them are linear combinations of the others, in the sense that, so for example, just looking at pairs of vectors, if one is a multiple of the other, then you can divide both sides by k, and then U would also be a multiple of V, assuming that we're not talking about the zero vector. So anyway, so three vectors are linearly dependent if one of them is a linear combination of the other. So for example, it could be that W is going to be written as, say, a multiple of U plus a multiple of V. And that exactly is the type of thing that we mean when we say a linear combination of U and V. So this is linear dependence. To say it another way, I'm going to say this one more way. Three vectors, U, V, and W, are linearly dependent So these are going to be linearly dependent if there exist constants, I'm going to call them C1, C2, and C3, that are not all 0, so that C1 times U plus C2 times V plus C3 times W is equal to the 0 vector. So 3 vectors are going to be linearly dependent if there exists a non-trivial solution to this equation. When I say non-trivial, what I mean is that of course the solution is going to be true if C1, C2, and C3 are all 0, but there's some other solution. So for example, if we were to have something like, let's look at some vectors in R2. So let's let U be the vector. I'm going to write vectors now as columns. So let's say U is 1, 4. V is going to be 2, 1. And W is going to be 4, 9. Okay, so W is going to be 4, 9. Now, these 3 vectors will be linearly dependent. Okay, well, there's lots of reasons why, but one reason right away that you can see why this should be is that it turns out that W is going to be 2 times U plus B. Okay, so in other words, you can write one of the vectors as a linear combination of the others. Or, equivalently, we could write 2U plus V minus W equals 0. And now we have a non-trivial solution to this equation. When I say 0, I should mean the 0 vector. So here we can take our, this is the quantity C1 U plus C2V plus C3W. It turns out that that's going to be 0, where C1 is 2, C2 is 1, and C3 is -1. In other words, this is the equivalence between these two statements. Okay? So if there exist constant C1, C2, and C3 that are not all 0, so that this sum is equal to the 0 vector, we say that the vectors U, V, and W are linearly dependent from one another. I should always emphasize that whenever we're talking about linear dependence or independence, you can never say anything about a particular vector by itself. It's always some relationship it's going to have to some other vector. Okay, so they will be linearly dependent from one another if you can find a non-trivial solution to that equation. So what that means, and this kind of leads us to our definition, I think this sets up the definition just a little bit nicer. We say that the vectors U, V, and W are linearly independent. So they're going to be called linearly independent if the only solution to that equation C1U plus C2V plus C3W equals the 0 vector is when all of the constants are 0. So that's only going to happen when C1, C2, and C3 are all 0. If that's the case, then the vectors U, V, and W are said to be linearly independent. Okay, and in general, this is the definition that's going to generalize for us. So just in general, the vectors, so the vectors V1, V2, all the way out to Vn. Okay, so this is going to be a statement that's true for 2, 3, 4, 5, 20, 100 vectors. But those vectors V1 to Vn are going to be linearly independent. So they'll be called linearly independent from one another if, again, the only solution to the equation C1 V1 plus C2 V2, I'm going to stop drawing arrows just for convenience here, plus Cn Vn equals the 0 vector is when C1 and C2 and all the constants are 0. Okay, so that's going to be If that's the only solution to this equation, then the vectors v1, v2, and all the way up to vn are called linearly independent.